All right, looks good, Ken.
All right, thanks. All right, hello everyone. This talk's going to be kind of a reviewing of the Science DMZ, looking at different various design patterns of the Science DMZ, different data architectures, and where also to locate your DTNs depending on the science and some of the engagement you may have with your users. So as we step into this, a lot of times campus utilization is broken down by, how can the infrastructure handle the users that are out there based on the number of users or the amount of demand that's out there based on capacity and, utilization in general. But, when you start adding, large research compute jobs and transfers and things like that, and how well can the campus infrastructure typically handle this? A lot of times, one researcher's job can actually dominate, and take actually more cores than an AVM infrastructure on a campus. In addition, there's also, more storage than an entire department. There's also more network capacity, the entire campus Wi-Fi, and that's just one researcher. Just depending on where, where these, folks are working and things like that, those kind of things come into play. Many times campus infrastructures are typically designed around what's called speeds and feeds of network access, number of services and VMs and to run servers, and also storage to facilitate those existing services. But a lot of times data is not really typically generated, from a campus, just from an enterprise perspective, unless it's more like database type functions and things like that. So, but a researcher might be able to generate multiple parallel data sets related to different types of analysis or different types of jobs that they're running to do their analysis on any sort of the work they're doing. And so a lot of times campus infrastructure is measured via uptime, availability, SLAs, and pieces like that. But when's performance actually measured? Most of the time, it's really measured after trouble tickets, and that's what we're kind of focusing on here. So if we, kind of change the paradigm a little bit to more of a performance first focused, the utilization will just come naturally. So some of these use cases, as you engage your researchers or you look at your flow data, those kind of pieces come up that who are your heavy users, and you can kind of address this accordingly. So many times data transfers look at something like this, where you have a server somewhere buried in the network behind a access layer switch in a campus closet, connected out to the core, out to the perimeter firewall through the border, and then it goes out to the world. And this works, it works for what it's intended to do, but many times the size of the data sets, the researchers really have a long time to wait for transfers to happen, or they have limited access to where the transfers can go to and from. There might be other bottlenecks, like some of the comments from the previous talk with Doug, some of the network troubleshooting, and some of these systems are like this, where a server is buried somewhere in the network, and you have to break down all the different components to get to and from the end-to-end solution to make sure that it's performant. And so a lot of times also researchers don't understand where they should be on this performance chart. What expectations should they have for data transfer performance and accessing certain resources and different data sets around the world, and even across campus, for example. So this is a chart that we have. We'll kind of review this a little bit later, but when you have a chart like this and researchers can see and understand, as well as IT services know where they should be performing at, that paradigm shift is something that can happen on both ends, so that really researchers and IT kind of understand the requirements, but also understand what the resources can do. So there's kind of a a happy point in the middle where you can meet and understand what each other's is offering and what each other should be expecting. So this kind of chart will help you get through that as you look through different resources. So going off the same type of thing, but why not both? So if you look at this, if performance was included in campus design, so that there were areas of the network, areas of the campus where where there are large instruments or large microscopes, sequencers, cryo-EM machines, or there was a new one I just heard about yesterday that's even bigger than cryo-EM. So that is doing something with 4D images and something else. But anyway, these producing, terabytes an hour of data. So be able to move that around a campus that's not prepared properly is really going to saturate functions or just take a long time. Or unfortunately, the researchers will dump everything onto a jump drive or a remote hard drive and carry it across campus. And that's the last thing we want, really, is going back to SneakerNet for these type of situations. So as you get into this, think of this, this is a slide I actually some comments in here I actually took from Jason. Think of this as a content as a reset. We don't want to build the IT for the sake of building IT. We want to tie the infrastructure back to the user and use cases and be sensible about design, installation, security, performance, and the operation. And one reference to this is going to a Science DMZ design and with the engagement of researchers. So the Science DMZ design, if you haven't seen this before, otherwise many people have seen this probably too much, but the design pattern is out there where for a large transfer to and from campus, you can put a high performance data transfer node either with local storage or connecting back to additional storage on campus that is really isolated down to only do the transfers to and from via security controls to and from the endpoints necessary or to and from the applications. Otherwise, the server is completely locked down from any sort of a random access. And by doing this, you take the heavy load off the firewall for these large data transfers, and you provide the data transfers to go to and from the remote site as it needs to and as performant as possible. So as we get into this, different campuses have brought up needs because not all campuses are the same. Not all border perimeters and border firewalls are laid out the same way. So we've kind of come up with a few different Science DMZ architectures to take a look at. And so we're going to go through this a little bit. And as we do this, we talk about the different components that go into a performance network or performance-based network, where you have a friction-free network path so that the high capable data transfer nodes can do the transfers at the speed they can transfer at and as they're tuned to do. These highly tuned machines can really send data out at a very rapid rate or receive data quite efficiently, more so than just dropping a server anywhere on your network. So paying attention to performance in this setup can really help out and really save time for the researchers, as well as create a nice security paradigm to know what's going on with this individual device and also with the data sets that are going to and from that server. In addition to that, the persona tools that Doug was going over earlier, having one of these at your perimeter will really help out to find, whether it, is frankly your problem or our problem. So that's where, if you say, having it at your border, you can test to the outside world, and if you're getting more, traction or more bandwidth out the other side, then it's not your problem. But if it is happening on your campus, then it is your problem. So just very simply having a single persona server at your border will really help you troubleshoot a lot of these problems. And then from there, there's multiple ways to put persona around your campus, depending on where you have large data transfers or you have performance criteria you want to be able to meet. It's really just a kind of a Lego block you can kind of plop down anywhere you want to. Then the other piece about a Science DMZ architecture is the engagement of the users. So understanding, where these researchers are and what kind of equipment they have, what kind of transfers they have, how large they are, how often they happen. All these things can come into a planning exercise and understanding, where you can, build out your infrastructure to be able to support this type of work. So those are the 4 pieces of the Science DMZ. And one of the previous directors at ESnet was looking at this, say, as researchers have their compute and they have their storage and they have their applications, a lot of times that what really is missing is the network is a major component of that. And it's kind of like the vascular system of the research workflow. So things cannot get from, one side to the other or from one collaborator to another without a network in the middle. So if the network is able to be created as an instrument as well and tuned properly, the same way you would adjust your compute and then adjust your code to compute more efficiently, or the same way you would set up your data storage to be able to be more efficient and be able to handle large files, small files, and the way you would tune an application, these all come into there. But a lot of times the network is often missed, and this, treating the network like an instrument as well, the way you calibrate it, could really go a long way to ensuring both data transfer times are reduced as well as collaboration between researchers. Another component of this breaks this down a little bit differently. The 4 components we talked about earlier, this is just a similar diagram to that. You can kind of see how they all mesh together. It's not just one piece that comes into this, but it's really a combination of various efforts to try to make this the scientific workflow more efficient, and then also help with the data transfers on a campus network to be able to be more efficient as well. So stepping into some of the designs, I have a few designs out through here for different data architectures we can take a look at. So we talked about this diagram a little bit earlier, just the basic simple science DMZ for large wide area network flows. And we talked about a few of the, I guess, benefits for having this. It's a very simple piece. There's very tight security controls you can put on each component. There's not a lot of hardware to deal with, just kind of is set up, it's tuned properly, it's locked down, and it performs very well. So going into this is where it gets a little interesting, is where every campus is different, every scientific workflow. I mean, there can be similar patterns, but until you have a researcher coming to you saying they have a problem, or they're getting this new piece of equipment, or they just want another grant or want a new grant, and it's going to be happening. So we need to figure this out, but you don't have all the requirements yet. There are various ways to kind of set up these, and these different data architectures are going to kind of go through that. So with this one, the way that an individual data transfer node can be set up by project. And so this doesn't have to be right next to your border router. You can actually, if you have fiber across your campus, you can actually home run the DTN at the local site back to your Science DMZ switch or router. And this will benefit in a number of ways, because you have a large enough switch and router to be able to handle the wide area transfers. In addition, you can actually try to get the data off the remote project and the remote location where the instrument may be set up. So this allows you to take the Science DMZ and extend it into a campus perimeter without really running across any other part of the campus network, and to be able to get data to and from the instrument. The downfall to this is you only have a single piece of equipment back at the edge. So there's just a single DTN can be connected there. Each DTN can have its own security policies and setup on there, but from there, this is just one example on how to do that. And I've kind of gone through some pros and cons here. Take a look at those. From stepping a little further is you have dedicated switches on each project. So you have the border router really building multiple Science DMZs out to these individual locations. And this could be based on data compliance, data policy, really a number of ways to do this. A dedicated instruments, it could be something like an open science grid cluster in one area of campus, and it could be a cryo-EM on another area of campus where you kind of have this distributed. One of the cons to this is you have to have multiple sets of equipment. So you need to have the Science DMZ switches and routers need to be able to have deep enough buffers to be able to handle these larger transfers coming there. So it's multiple large sets of equipment that you would have to support, but at the same time, these are developed around different security profiles and different data transfer sets that can get into it. See here for anything else. Again, this keeps the large science flows off your campus network. The DTNs can be custom tailored for the actual workflow on the job. So another design that some folks have looked at is how do they connect their HPC so that they can integrate persona and data transfer nodes, a parallel file system to some of these locations. And this was a slide that was set up to kind of address all those individual pieces like that, related to this, using the Science DMZ design pattern and including all the 4 elements related to the Science DMZ architecture. And getting into this, you can see how there's multiple switches there, there are multiple data transfer nodes connected to the parallel file system, and you see the supercomputer and the way that it's set up there. Another approach that's similar to this is if you break that down a little bit further, and then you keep your campus compute nodes and your file system back on the enterprise network or back in your data center network, having individual file and security controls based on this data, you can actually engage the Science DMZ pattern so that you create a cluster of DTNs on the outside, so that these cluster of DTNs will provide you resiliency, provide you scalable bandwidth related across the data transfers, as well as if you need to take one down for maintenance or patching, you still have the other ones there available to do this. So this was a way to set up cluster DTNs connected to the parallel file system or remote storage that allows you to kind of address all the needs, maintaining the Science DMZ design pattern, but in addition, creating some isolation between your cluster and head nodes, so they're not really on the outside world. Having people log into them from the outside, those would still go through your campus and your perimeter firewall. One thing about this too is, on the pros on this one, you don't need to do the double copy. So when you're first starting out and you put a DTN on the outside with local storage in it, you might need to copy there the first time, and then you might need to copy onto your local campus storage a second time once you get the data to your DTN, then pull it back into where your compute and storage might be located, or towards some analysis machine locally on campus. So that kind of piece, preventing the double copy transfer with this cluster DTNs really can go a long way to increasing performance and cutting down speed. And frankly, a double copy workflow is sometimes still needed, but this is the way you can kind of get around that. So the other piece around this too is you kind of separate out your data transfer node and you create the data transfer portal and put that inside the campus. And then you only have access to the data transfer nodes via the API to the application. So we're going to go over that in a little bit, but this model here with the cluster DTNs allows you to separate out the data portal on the website from the actual data transfer process and the data transfer application. So as we get into this is a similar diagram I had from the beginning, where you have your portal server based somewhere within your network, going through the enterprise network, through the perimeter firewall, and stepping out through there. So as you get into this next generation portal leverages the Science DMZ data transfer pool as well as a central data store. So how this comes into play is the DTNs themselves only have API access to the outside world. There's no other way to get into them unless an out of band management or something, but the actual outside world, only the API can access those. So you initiate a transfer by going through the wide area network, down through the perimeter, down to the portal server down here. And this can even be a container-based solution at this point. And as you're doing that, you request your transfer. It kicks off an authentication and a transfer job process. And then that comes down to the DTNs, that gets coordinated, and then you can do your data transfer back and to and from your file system through the Science DMZ. So this is your request and your authentication path and authorization path when the actual data transfer kicks off this way. And there are a number of public examples of this working, and it works very well and it works very efficiently by separating out the two components of your data transfer nodes and going through those pieces. So just again, more some pros and cons here if you want to look over those later. Another data archive to take a look at is if you have a large instrument on campus and you need to be able to set up and understand how to get data to and from that instrument. Sometimes the least equipment that comes from a large instrument is pretty locked down, and you need to keep it on a private network because the patching for it is sometimes not as efficient as you want it to be on these control PCs. So what you can do sometimes is create a pass-through directly to that, where you have the storage actually land on the data transfer node or the actual shared storage itself. And you can kind of use the Science DMZ design pattern inside of a campus right next to an instrument so that you can make the transfer more efficient versus just using, a lightweight, say Windows machine here that will run, will control the instrument, but is really not able to handle the transfers very well. So if you mount the drive back to one of these other locations, the data transfer node can be the efficient way to move the data around campus, whether it's out to the outside world or whether it's back across campus network towards your HPC and your centralized compute versus your local compute here. So again, these are like Lego blocks that you can keep working with depending on where your bottlenecks are, where your transfers are, and then being able to understand to and from, where the transfer is going and what the researchers need. So two other pieces that have come up through EPOC that are pretty interesting is sometimes people believe that the Science DMZ needs to be a separate, research network that's parallel to the enterprise, that is completely air gapped, or they only connect up with the border router. And then, but desktops and NAS systems and compute nodes and GPU machines are all sitting on this, this public research network that's out there. And a lot of times this is really limited to only research and education networks. So it limits access to cloud and other services, like GitHub. And this is typically it's unusable. Some people have complained that while they can do certain things very well, other basic functions they can't get done. So one of the recommendations was just to try to integrate this existing research network with your enterprise network to make it more usable, and then re-engage and refactor your Science DMZ for the transfers. So it's not really taking anything away. It's just looking at what you've deployed and then refactor this to make it more usable, as well as secure, but also make it more performant at the same time. Another use case and example is some large campuses operate more like an ISP, where they have central IT and they have distributed IT and the local areas, the research areas, as well as administrative functions. So the IT support is very disseminated across campus. And looking at this, you also have border firewalls, you have separate data center firewalls, you have firewalls in front of wireless, you have firewalls in front of campuses and different departments. So even to try to get data off an instrument like a cryo-EM across campus can be somewhat difficult at times. And one researcher actually was just stating that the transfers off campus to another collaborating university were faster than transfers across campus within the same segment of the campus, a few buildings away. The transfers are different. So numerous MTU mismatches were found on the networks. So the recommendation was, to tune for the jumbo frames and you try to build a Science DMZ pattern that works to bypass the data center firewall and allowing only the traffic from the DTN for the cryo-EM to be set up. So these are again different use cases that are out there to take a look at. As we step into this with the different data transfer nodes, the original design was back in 2012. I think the concept had been, 2010 to 2012, there were different presentations and different setups as we started discussing these type of design patterns. The idea is really around the server is really designed and built to do data transfers directly, nothing else to do, and that's it. So as you get into this, the different components around there, you limit the application, you limit the security profile on the outside. Then as you get into this, the other piece is typically you can have local storage on there, but you can also connect remotely to remote storage. So as you get into this, the other pieces come into play where the DTN and the persona node, you can set these up directly right on the security or the router at the border, and make sure you have all the components within the Science DMZ for this. One thing about this, a 2 10 gig server, as we're finding, is actually much more efficient than just 25, 40, and 100 gig servers that really are just plugged in. There's a lot of tuning that can go into a server that can make it much more efficient. So you can save quite a bit of money by going with a 10 gig server and have it tuned efficiently back to a central storage, and then going from there. Multiple DTNs, like we talked about earlier, cluster DTNs together can perform quite well, but also provide you some resiliency. So instead of spending a lot of money on a single 100 gig server, 2 or 3 smaller 10 gig servers can perform, much more efficiently, as well as provide you some downtime. But the key takeaway here is to make sure you match the DTN capabilities of the site and the wide area infrastructure, as well as what the researcher may need. Some of the other pieces around DTN considerations to look at, you want a single resource for moving the data to start with, and then working with individual researcher or an individual project. So from there, you can step this up, and then you look at try to get a NIC that you can find that works for your campus. Typically a 10 gig, like we mentioned earlier. Some sites are starting to go from 40 down to 25. It's more common on newer switches and within data centers. In addition, you want to try to have direct connectivity to the outside, as well as a faster clock speed for your DTNs. Multiple cores, usually 8 and up, allow you to run parallel transfers at the same time to be more efficient as well on the data transfer node. And then again, make sure your storage is allocated appropriately, whether it's local or with something tied to something on the back end. Here's an example of a DTN we just actually put online in the last 2 weeks. So some of the numbers there you can kind of look at and look there. And then I included a URL at the bottom if you actually want to test transfers to and from this DTN. So we talk about data mobility benchmarks. So this is something that on the data mobility breakout room, we can kind of go over, and I have a separate slide deck for that. But what this allows you to do is really test and tune your data transfer node in your Science DMZ, including your perimeter, to make sure you're running the appropriate BGP path, and also testing your storage read and writes. So these are a series of links you can go out and to click on and try to run these, or you can see me in the data mobility breakout room and we kind of step through a few of these and try them out. One of the final things here is we have a data transfer scorecard that we're trying to work through and try to get people to understand this. So with EPOC, we're trying to make sure that researchers can transfer at least 1 terabyte per hour. And that turns into roughly 2.2 gigabits a second, or from a sysadmin or storage perspective, 277 megabytes per second. So having those numbers, depending on the audience, will really help us understand kind of what each other's language we're speaking. But really the baseline is we're trying to focus on, to the researcher, 1 terabyte per hour is a baseline to start. And then from there, you can kind of do some tuning and try to increase from there. But if you're not getting these numbers, please, give us an email, give us a call, so we can help you with these transfers. But this is kind of the baseline we're trying to work from to kind of raise all boats, if you will, so that everyone can be more performant when it comes to these cyber infrastructure grants and the implementations we're doing to support our researchers. Some of the other pieces around Science DMZ and DTN tuning you can take a look at. The MTU is the biggest problem we run into. Mismatched MTUs, like Doug alluded to that earlier in the person talk. And there's a link here to an EPOC paper on the MTUs. Adjusting your BGP to prefer research and education networks. This is a big one, so that your traffic doesn't go out and go over commodity networks. Running traffic through, like, for example, NYSERNet is typically more efficient than your commodity network, depending who your provider is. Setting up persona on your border router, we mentioned earlier. Research the modern research data portal, which I covered a little bit ago, about separating out the authentication authorization in the portal website from the actual data transfer services. Something else you can also do is set up top 10 source and destination reports to keep your eye on large transfers, who your large transfers are happening to and from. If you don't actually have tools to do this, you can probably look at your NetSage instance, either from your regional network. They may have access to this data and be able to help you troubleshoot who your large users are with the transfers. Again, well-tuned 10 gig servers go a long way versus a single 100. And one other piece around restricted and controlled data, if you must have something behind an enterprise firewall, to make that more efficient, a lot of firewalls have what's called an ASIC-based transfer path. So sometimes they brand that as fast path or express path, depending on your firewall vendor. So this is a way you can still make certain conditions go through the firewall, even if they need to be able to go in a more efficient path. And then I also included a link here for DTN tuning. So. Yeah, so any questions?
So thank you, Ken. We did have some questions that came in during, but we hammered down most of them now.
Okay.
There's one that's coming in right now. I'll just read them and you can answer them. Okay. Is fast path similar to cut-through switching?
No. Cut-through switching is really on the data center side. It's really we've run into a few issues with people buying data center switches and plugging them into their Science DMZs because they don't handle large transfers very well, and they usually have dynamic buffering within the switches. So the transfers can really be affected by cut-through switches. The ASIC-based pass is a firewall process. Once it checks the data transfer, that will run it directly to there and not process the rest of that flow. So that's just a few things we've run into in the past, and just a recommendation for looking at those type of things. So.
Okay, and we'll get one more, and then we'll need to transition to the next one. Any new alternatives for BBCP? BBCP is the I want to say it was developed by Slack, but it's sort of similar to grid FTP in nature.
Yeah, typically a lot of for the data portals and things like that, typically we use the Globus next generation portal with the Globus system on the back end for distribution of data. For bulk transfers, there are a number of tools out there that can be used, but typically there's a number of ways to use the Globus API to automate workflows related to things like this. So if you're trying to make something more programmable, and I think Globus has a new system called Flows, you can plug that in there and actually make things like that work much, quite a bit more efficient. For the actual transfers themselves, I mean, there's a number of tools out there. It just depends on the frequency of the transfers, the authentication, who's going to get them. There's a number of, there's a lot of variables in there. So and there's also a lot of tools. It's just, I guess I'd say pick what works, but typically if you're trying to set something up for, data coming off of cryo-EM, set up the Modern Research Data Portal with the Globus API, and you're kind of done. So.
Okay. And just a comment, send your slides off to Jorge and his team so that they can get them posted, because several people have asked.
Yep.
And with that, I will hand it over to Jorge to transition to the second hands-on session.